We talked a lot about creating token IDs, but now let's take it to the next step and talk about creating token embeddings. So if I go back to an earlier figure from section 2.2, we looked at this figure where I showed you that input text gets converted into tokenized text and the tokenized text gets converted to token IDs. Now the next step is creating these token embeddings from the token IDs. So essentially taking an ID, an integer value, and converting it to an embedding vector. And so this embedding vector contains real numbers like floating point numbers that can then be optimized. So to show you how it works, we are going to use some token IDs as an example, just like as a PyTorch tensor, so that it is a bit more easy to see what's going on. So let's do torch tensor and then insert those. And I should say these are relatively large numbers. So let's actually use some smaller ones so we can have nicer visualization. So these are just like some words or tokens in our input. So we have this input tensor now, and then the next step would be creating a so-called embedding layer. Usually this embedding layer is part of the LLM itself. We will revisit this many times later in this book, but this would be a standalone embedding layer. And there's usually something called the vocabulary size. So this is the size of the tokenizer, the vocabulary tokenizer. And then the output dimension. So this is the vector embedding size. So the vocabulary size is, in our case, for the tick token tokenizer, it's 50,257. Sorry, that is probably not the correct number. Let me double check actually. Tokenizer. One way, if you forget, like me, what the name of the vocabulary is, you can use in Python this dir, and it should actually show you. So n vocab. So if I go up here, type n vocab, and then we do the length, you can see, oops, it's not a list, it's just an integer. You can see it has 50,257 unique tokens. So this would be one argument for our embedding layer. So it supports all these different tokens. And the other one would be the output dimension. So this would be the desired size for these vectors. We will actually use the original GPT embedding size later on. For simplicity, let's actually use simpler and smaller values, so it's then easier to visualize. So let me use vocab size 6 and output dimension. Let me just copy it. Let's do 3, because 3 is also what we are seeing here, like 3 little boxes per vector. So we have a very small example that is hopefully easy to see. And then one more thing is I'm adding a random seed here. Why am I doing that? It's because this is a neural network layer with random weights. And so the random weights are different each time you instantiate a new layer. And so I just want to make sure you get the same results that I do. So I'm initializing this random seed. And by the way, if random seeds are something you are not familiar with, let me know. I also have a nice video on random seeds I can share with you. But yeah, so this is now this embedding layer. And the embedding layer has a weight matrix. Weight. And so this is something that is later optimized during the neural network training, like the LLM training. And they are called weight parameters or parameters. And these are things that are going to be adjusted. And by the way, if you are familiar already with linear layers or matrix multiplications and everything, an embedding layer is just an implementation detail to make a certain lookup easier or more efficient. This is more advanced. You don't have to read this if you're not familiar with this, but for those who are curious, I do actually have some bonus material here where it's about understanding the difference between, the difference between embedding layers and linear layers. So if you're curious how this relates to matrix multiplications and linear layers, it's like a short notebook for those who are curious. But if you are not familiar with it, don't worry about it. I will try to explain it in a more, let's say, intuitive sense. So let me show you something. So if I do embedding layer and I call it on, let's say, this input here. Let's just pick one of these numbers, torch tensor. Let's make a smaller tensor and use, let's say, the 3 from here. Let's see what happens. So you can see it's pulling out a vector here. So there's a tensor of 3 different numbers. And if you have a sharp eye, you might notice it's actually this row here from this embedding matrix. So if we are typing 3 here, Python is a 0 indexed. So it's 0, 1, 2, 3. It's giving us this vector from this matrix. And similarly, if I go here and I do, let's use the first one, and I do this one, you can see this one is the first, sorry, not quite, the third row, sorry, 0, 1, 2, because that's the number 2. And this is, yeah, the index 2 corresponding to this row. And similarly, if I now use the whole input IDs, I'm pulling out values from this matrix. So I probably should show them here for reference. So the first one, that's the 2, it corresponds to 0, 1, 2, to this one here. The second one corresponds to this 3, so this would be this row here. The 5, this one, 0, 1, 2, 3, 4, 5, and so forth. So we are essentially, when we are calling this embedding layer on the input IDs, we are pulling out vectors from this matrix. And this matrix technically has the size of our tokenizer. So I can just show you this example, tokenizer.n vocab, right? So in this case, this might be a very large one. Should I print it? Maybe let's try and see what happens. It's actually dotting it out. But yeah, this would be then 50,257 rows essentially. And yeah, this is essentially the embedding layer that is used to convert the token IDs here into these vectors. And this is usually part of the LLM. And yeah, these numbers I mentioned before, they are random. So if I actually comment this out, you might see these numbers change because the weight matrix, the weight matrix changes. And so usually what we want to do is we want to start with small random numbers. It doesn't really matter what these numbers are, but later on during the training, these numbers get optimized in a sense that the LLM is optimized end to end to produce the desired text, the next word in the training text. And so don't worry about why these numbers are random yet, because they're not trained yet. They're just starting values. We're going to train them later in chapter 5. But now, you have a hopefully good understanding what an embedding is. So an embedding is a vector from this embedding matrix that gets later trained.
Get this book at Manning.com.